So, okay, what did we do last time? Thanks for coming back, by the way. So last time we did MDS codes. MDS codes, and we looked at this, and we derived some generic properties of these things if they existed, and then eventually we moved to Reed-Solomon codes. And so indeed they exist. We talked a little bit about existence altogether, the main conjecture on MDS codes. I just wrote it down. And like I said, you want to be rich and famous, solve this. There's people doing geometry in math that would be deliriously happy if we solved it. So for nothing else. So the last thing I wrote down last time was something about a matrix which somebody recognized as some Fourier transform matrix. And that's where I want to pick up here, at least quickly make that connection. So let me rewrite the definition of Reed-Solomon codes again. And so a Reed-Solomon code, the way we defined it last time was with all field elements. We would evaluate the polynomial in all field elements. Now we do it slightly different. Let's make it Solomon star in order to denote that difference. Let's say this is beta 0, beta n, so that's the old definition, only the, let's say the beta 0, beta 1 up to beta n. They are the non-zero elements now. And just for the heck of it, so we talked about punctured Reed-Solomon codes last time, that this would still be MDS codes, so nothing has changed there. In particular, all the arguments would be the same. In particular, just to humor me, let's say beta I is omega to the I, where omega is primitive in FQ. So what that means, you remember that primitive means that the powers of omega cycles through all the non-zero elements. Right, remember the non-zero elements are a multiplicative group, and it's a cyclic group, and it's the generator of the group. Okay. Good. So once we write it like this, we can actually write down the whole Reed-Solomon code in some sort of transfer domain description in a Fourier transform. And the way this goes is the following. So from now on, I will make implicit identifications without making them. So this is an identification which I just jump around between a vector. So this one would be in FQN. In FQN, and Fx would be maybe 1, no, maybe 0 to n minus 1. So, yeah. All right. Yeah, okay, let's leave it at that. So I make this. Yeah, let's make this identification free, right? It's just a vector of length n and a polynomial of length n. So whenever I want this to have a low degree, the polynomial, then I will write that explicitly. Okay, so this identification we make freely now. And then how can we write f? Let f now be a code word in the Reed-Solomon code, and then I say fi. What is fi? The ith element. Well, we know that this is f of omega to the I, right? So all indices are for the moment counted from 0. So this is, if you write it out, f, maybe j, omega to the I to the j, which is omega ij. Right. And now at this point in time, everybody recognizes this. Right. This would be the discrete Fourier transform of a vector. This is an element of order n. Right? Like usually you have e to the j and then an element of order n. Now it's in the finite field, but what's the difference? Still, this would be the Fourier transform. So a code word would be the Fourier transform of a vector f. Right? Let's just make sure it also goes the other direction. So I claim that FL would be, so what would be the Fourier transform? If it indeed is a Fourier transform, there's a minus, and then it goes n minus 1 fj omega minus jl, right? So the question is that true, right? Because that would be the inverse. Is that true? Oh, let's do what we do with proofs of this type. I need that space here. What? Yeah, so let's do what we do with proofs of this type. That means we write it out. There's another beautiful thing about finite fields. You never have to worry about convergence. Right? So for the f, we just plug that in here. This would be, what do we call it? Fi, or yeah, Fi omega to the I j, right? So this would be Fj, and then I want omega minus Jl. So is that true? Is that identity now true? Well, we see two sums. What do we do with two sums? Feel compelled to exchange the order. That's always what we do. So Fi goes out, and then we get omega to the, what do we do? I minus L times J, right? We have this. And so what is this? How can we work this out? Well, you know how to express the sum. So this part of the sum is really just omega I minus L to the n minus 1 minus 1. Well, that's a standard formula for summing these things up. But omega is an element of order n, right? Omega was an element of order n. That's how we chose it. Is what? You multiplied omega. It's primitive in the field, so omega, we have omega I unequal to 1 for all I less than n, and omega n is equal to 1. So, okay. Yeah, right. That's fine. So it's an element of order n. That means the nth power, if we can interchange this. So this is 1 to the some power remains 1. So 1 minus 1 is 0. The denominator, well, actually we get two results here. If I is unequal to L, right, then this is 0. If I is equal to L, then this one here, if I is equal to L, then this was just the sum of n ones. All right, so we get n here I equal to 0, but n was q minus 1, the multiplicative, the size of the number of non-zero field elements, because it was primitive in the field. And this one is just minus 1 in the field, because q, we compute q is the power of the prime of p. So that would be 0. It would just come out as minus 1. That explains this minus here, and we can get rid of the question mark. All right. Is that correct? All right. According to popular vote, it is. So what do we really have here? We have everything we want from a Fourier transform, right? We have a Fourier transform pair. We have a vector f, which we can think of as being in the frequency domain. Then we have a vector f. So this, which is a Fourier transform of that. This one would be in the code if the degree of this polynomial here would be less than k. Right. So now, how can we understand Reed-Solomon codes now from an engineering point of view? Classical. What about band-limited functions? What do we know about band-limited functions? Because in a sense, the degree less than k. This means that fi is 0 for all I greater than k. Right? That's what it means. So, in a sense, it's nothing but a band-limited function if this is a frequency domain. If you consider this as a frequency domain. So what do we know about the band-limited function? Well, if a function is band-limited, it cannot be impulsive. Right? We know that. I mean, the support of the frequency in the frequency domain sort of inversely relational to the support of the function. So the whole idea of Reed-Solomon codes, in a sense, can actually be understood, at least intuitively, from Fourier transform and the duality between time and frequency. Yeah.
What's Q a prime?
Q is not prime. Q is the power of a prime. P to the n.
So there's always a primitive.
There always is. Oh, sorry.
Or because for any Q there will be always a primitive.
Why there is always a primitive element in the field? Yeah, sorry, I thought you had gone through that. It's because the non-zero elements in a field always make up a multiplicative group. And it's always a cyclic multiplicative group. It's always a cyclic multiplicative group. And it's just the generator of that group. Right. It's the same statement as saying a cyclic group has a generator.
If SQ, for example, was ZQ,
yeah.
Then Q has to be prime.
Yeah. In order for it to be a field, Q has to be prime, right? That's true. But we are not worried about this. This theory is. It's also a beautiful theory, codes over rings. If this would not be a prime, very nice theory. It becomes a little bit more technical. Actually, more technical than more difficult. Okay, but this is. I just wanted to give you this correspondence on the Fourier transform because it's sort of, from an engineering point of view, a very nice insight. That one of the reasons one can understand that Reed-Solomon codes have a good minimum distance is because there's a transform of a band-limited function. Right. All right. So that's what I wanted to say about the Fourier transforms here. I do not want to spend too much time. I have to get through decoding here. But it is, since we have now this Fourier transform correspondence, we can do another thing. We can namely say, well, f is in the code if and only if the Fourier transform, so that was the back transform here, right? Right. So we can also now the code word, we can interpret the code word as a polynomial, and the inverse transform is just evaluating it at an omega again. So we can, f is in the code if and only the transform of a code word is 0 for all I greater than k, up to n minus 1. So, yeah. So it basically just means the support. The function has to have, if it's band limited, right? If this one is band limited, then this one cannot have arbitrarily small support. That's what it means. Right. That's really all I wanted to say. I greater than k and less than n. So we have that f is in the code if and only the polynomial evaluates to 0 at a bunch of points. Now that leads to something interesting, because now we can say, well, so what if we just construct our set of vectors f so that they evaluate to 0 somewhere where we want them to 0? We construct them somewhat differently than here. And in particular, let's define G as a product of I equal to k up to n minus 1 of x minus omega minus I. So it's a polynomial. This is a polynomial, right, which satisfies this. Right? So in particular, we have G of omega minus I is equal to 0 for all I less than n, and greater than k. Right? So this is a code word, right? You agree this is a code word? Good. So we found a code word without going through this here. I mean, without going through the evaluation map. We found it straight away. But not only did we find this, this has degree n minus k. Right. This has degree n minus k. So maybe there's another interpretation. Now we can give a whole new definition of the Reed-Solomon code, namely as a set of polynomials. As a set of polynomials, which are sort of implicitly identified with a set of vectors, such that times this g of x, right, and h of x is less than k again, right? So what we have here, it's again, we take a vector space of functions, the h, right? It's a k-dimensional vector space, and we multiply it with this g. It's again a linear map, this multiplication with a fixed polynomial, right? A linear map of this vector space gives us again a vector space of dimension k, and all elements in this vector space evaluate to 0 for all omega to the minus I. That's just the same again. Just the Reed-Solomon code again. So it's a very nice complementary description to the same Reed-Solomon code we could define up here, we have found again down here. What is so nice about this? Yeah, what is so nice about this? Yeah, what do you think is so nice about this? About this description? So now you have to think as engineers, right?
You can split evaluated, there we have to evaluate it at endpoints of function.
This is, yeah, exactly. This is so easy to implement. Right, so now we think a little bit about encoder. An encoder for for a Reed-Solomon code. How would we do that? You look at this here. Hey, let's do this. Let's exactly do this. Meaning in VLSI, we do something like and here you would write in, this is just a delay element. This one would be G n minus k. This one, right? So these would be the coefficients. This polynomial we can evaluate once and for all. We do that once before we start our communication. We evaluate that polynomial once and for all. We know these coefficients. So these are multipliers which multiply with those corresponding coefficients, and we feed into here the coefficients of this polynomial. These are our information symbols which we simply feed into this circuit. Right. And into this circuit, out comes f. Out comes the code word. Polynomial multiplication. If you show that to a VLSI designer, they are deliriously happy. I mean, they say, you know what? I implement you this thing. I implement you in 5,000 gates, which is close to nothing nowadays. And there, maybe not, maybe 10,000. And there we get to the second reason that Reed-Solomon codes are so extremely important in practice. On the one hand, they are MDS codes, meaning they are about as good as it gets, right? And on the other hand, there are algorithms, there are circuitry for these things, whose cost is close to nothing, right? At least today. When they were invented, that was quite different. In the 60s, that would have not been implementable with transistors on a board or something like that. But today, the cost is close to nothing. So the whole algorithmic treatment of Reed-Solomon code is very well developed. The encoder you could do like this. Yeah?
Why do you still require that degree hx less than k?
You don't need to do that, but then the mapping is not one-to-one anymore. Then the mapping is not one-to-one anymore. Then, okay, let's put it other ways. If you want code words of length n. If the degree is larger, you run over. In order to still get a code word, then you have to take it modulo x to the n minus 1. And that would fold the coefficients back. It still gives you a valid code word then, but this is not one-to-one anymore. Right. Anyway, the short answer is if you allow more, then they become longer than k, longer than n. Okay. So, what's the time? Okay. So this is a nice encoder. There even is a nicer encoder, which I just want to give the formula for. The one reason that people still have a problem with this is it's not systematic. Well, people like to see the symbols in the code word themselves, right, the systematic part. How could we achieve that? Well, we go from the same description here, and we say, well, let h of x be given, and compute x to the n minus k times h of x modulo g of x. So we divide this polynomial by this polynomial g, or it has a name, it's called the generator polynomial. We divide it by g, and out comes some polynomial r of x, right, of some low degree less than g. Right. And degree r of x is less than n minus k in particular. So, and then we can form a code word, I claim f of x. No, f is, and here we write r, and here we write h. The coefficient vector of h and the coefficient vector of r. Why is that a code word? Why is that a code word? Maybe minus here. I always think in characteristic 2 anyway. So why is this a code word? Anybody? It's clear? Or what this is in terms of f of x is r of x plus h of x. Right? That's because, or minus r of x maybe. That's because we wrote it like this. If we now take the f of x modulo g of x, well, this part has degree low. It's not affected by this modulo operation. This would be minus r of x plus this one modulo g of x, which is r of x. So the whole thing is 0. If this is 0, that means g of x is a factor of x, of f. Hence, it's a code word. So we have a code word here, and in the code word pop up our symbols right away. Our encoded information symbols right away. So we get some nice systematic encoding going. This division circuit by G is pretty much the same size as this. It's not larger at all. So there we get beautiful algorithms. This is actually what's implemented. If you go to any disk drive or so, that is usually what's implemented in there. Exactly this. Okay, algorithms. Algorithmic treatments of Reed-Solomon codes. Do you have any questions about any of this? Yeah?
How are these Reed-Solomon codes mapped onto the Euclidean space?
They are very coarsely mapped. Usually, it depends a lot on the application. If you think disk drives, they are just being mapped. You take Reed-Solomon codes over a characteristic 2. Then each field element is represented as a vector, as a binary vector. And that binary vector is mapped into on-off keying. Straight off the bat. Nothing more fancy. That is for disk drives. And if you do, there's a satellite standard where it's mapped onto the 256 QAM field elements pick out. So it's many different ways. Many different ways.
No, but to prove some performance bounds on the RS codes, we need to have mappings, right?
We need to, in order to prove performance bound, we need to have mappings. And the Hamming distance bounds that we get from here give you bounds on the minimum Euclidean distance. If these are good bounds or not depends a lot on the modulation scheme. And to be perfectly honest, they usually are not. They usually are not very good, the bounds. But it's a very difficult problem to design a code or to find a representation of the field that maps nicely onto a modulation scheme. Very difficult problem.
How do we know by looking at this that this is a good code?
The code itself is excellent in terms of MDS, the MDS property.
Why does MDS mean good to us?
In respect to modulation,
Yeah.
it doesn't. It doesn't. There's, let's put it like this. It's not easy to define, it's really not easy to define codes in Euclidean space. So all that we do is we find ways to do that and guarantee some performance. Right? Some sort of performance. It's not easy to spread out, I don't know, 2 to the 1,000 points in 1,500 dimensions. These would be typical numbers, really. It's not easy, right? And since that problem is practically daunting, it's a daunting task. We have to develop all sorts of crutches to do that. And this is really one. So outer code, MDS codes, playing a part in this mapping. If you want to be more fancy about that, then you put a convolutional code or some other code also in there and do a combined scheme. I think Professor Forney will talk about that more. So here's just the coding theoretic groundwork of these things. All right. Anything else? Yeah?
On the first line, it is beta n minus 1. Very first.
Yeah. Thanks. Okay. So the algorithmic treatment of Reed-Solomon code is extremely elegant, and that's the second main reason they are so much used. It doesn't cost so much to implement them. Well, at least we've seen that for the encoder, that's a fairly small circuit. So what about decoding? Decoding. How do we decode these things? How could we possibly decode them? And I give you a... Right, that's true. We could do the Fourier transform, but it doesn't help us so much. So we take because we receive something, and we receive a vector, say y, and this vector is, from now on, let's say x is a code word. RS, right? So x denotes usually a code word from now on. So this is a code word plus an error. So in particular, if we take the Fourier transform, we take the Fourier transform of the code word, which is fine, but then we get the Fourier transform of the error. So that sort of destroys all the fun. What else could we do? Here's typical parameters of a code. 255, 239, or 256. And you immediately see that any sort of brute force is out. Right. We have, how many code words do we have here? We have 8 to the 239 code words. Now you don't want to search that. You definitely don't want to search that. So how could we possibly decode these things? Okay. Turns out to decode them in some sort of optimal fashion, maximum likelihood is actually, it's an NP-hard problem. It's been shown, maybe last year actually has been shown, that it's an NP-hard problem to decode Reed-Solomon codes. It was known that decoding in general is NP-hard, but this is now the constraint to Reed-Solomon codes is still hard. So what do we do? Yes, okay, what do we do? Let's say x is a code word, we know that. And set weight E, let's just call it T. All right. So what happens if we don't have an error? Right? Just thought experiment. Thought experiment, if we don't have an error, then yi in all the positions is equal to f of xi for some f of x of degree. Okay. So, all right, good. In particular, since we know the axis, we know the positions, right? Sorry. Sorry. That's not what I wanted to write. This is definitely not what I wanted to write. Let's keep that as C, as a code word. And position I in C is associated with xi in the field. So meaning Ci would be f of xi. And that's really what I wanted to write. Makes more sense. Okay, so thought experiment. No errors. Then yi is f of xi for some f. Right? If there were no errors, then we could just solve this linear system of equations, right, to find the coefficients of f. And the coefficients of f, say, were our information symbols. Is it clear that this is a linear system of equations? Yeah. It's sort of, you could write it out as y0, y1, y2 equal to, here we have f0, f1 up to fk minus 1. This is a linear system of equations. We know the xi's. This is the linear system of equations we have to solve. Okay. So, yeah, if there are no errors, then life is easy, right? That seems to be reasonable. So what happens if we do have errors? Somehow we have to make sure that the errors that we get do not cause any problem for us. And then we do something very ingenious. We define something called an error locator, which is a polynomial x such that x minus xi. So it's a polynomial which is 0 in all error positions. Right? Well, I mean, you might say we do not know the error positions. Well, okay, that's true. Basically, this is in the end what we want to find, this polynomial. But nonetheless, this polynomial exists. Right? And so we can cast actually the coding problem this is form 1 as this one?
The error is a field element.
Yeah. Right. Error is a field element. Yeah, it's an additive error model. But you can cast pretty much anything in this. Right? If a position is altered, you can always model that as if something was added to it. Decoding problem 1 is find lambda of x of minimal degree such that lambda of xi is 0 for all xi and degree f less than k. So I claim if you solve this problem, right? Namely, this is a problem I give you a vector y, right? I give you a vector y, here it is, here's a vector y, and I give you a vector x, which corresponds to the field elements where you evaluated that in order to get the code word. And then I said, given y and x, find two polynomials lambda and f, such that f has maximum degree k and lambda has minimum degree, the smallest degree possible, so that this is true. And I claim this solves the decoding problem. Right, this would solve the decoding problem because once we have found this, then we can take lambda to be the error locator, and we can basically read off the information symbols from the f. Okay, good. So this decoding formulation now brings it at least into the algebraic realm. Right? Brings the whole decoding problem, makes it something algebraically. But now the question becomes, is that easy? Or can we do this problem here? Is there do you see any hope for solving this problem? I guess the only answer that okay, anybody does not see any hope. All right, this is great. You all see hope here. You all see hope here, which seems to make you an opportunistic bunch. And not opportunistic, what's the word? Optimistic bunch. Let's put it like this. What is the problem in solving this? It's not linear. You get the coefficients of lambda, multiply the coefficients of f. That whole thing becomes a nonlinear problem where we say in the end, find the zeros, or find a solution to a set of polynomial equations in a field, right, which is multivariate polynomial equations, where the coefficients of lambda and f are the variables. You can do that. You could use techniques like Gröbner basis or so, and you could do that. But this is very difficult. This is computationally tedious. Okay, so is that clear why this is nonlinear and why this is hard to solve a nonlinear problem here? If not, then you have to say something now or forever hold your peace. Okay. So what do we do with hard problems? Right? Once you take the optimization classes, there's almost like a reflex. There is a relax stamp. We find the proper relaxation of the problem. And the proper relaxation of this problem is the following. Coding problem 2. Find lambda of x of minimal degree, such that, and it's almost the same, lambda fi yi minus h of x I is 0, where the degree of h is less than k plus degree lambda. So all that we did from this formulation, which would give us a clean solution to the whole thing, right now we multiply in this lambda, right, which gives here, it keeps the lambda times y, and here we get a new polynomial, lambda times f, which now has degree at most k plus degree lambda, right? And then we say, let's instead solve this problem. And let's solve this problem. In particular, the question now becomes, well, we do not require this anymore. In this relaxed formulation, we do not require this. And that makes all the difference. It makes a world of difference because this one, look at it, it's a linear problem. It's a linear problem, right? Why is it a linear problem? Do you see it's a linear problem? Right. Could you write down the equation, the matrix equation? It's pretty straight, right? It's pretty straight. You could, for example, write it like here, a diagonal matrix yn. Here you would get something I think that seems to be all right. And here just the evaluation of the h. So up to h k plus degree lambda. Right, it's a linear system of equations And we can certainly solve this. Well, we do not know really what the lambda is, what degree the lambda has, but by just hypothesizing on all the possible degrees, we could solve that for at least, well, we could say, okay, let's assume the degree lambda is 0. It's a constant. Which would be the same as saying there are no errors. Right? Then we can look at the system of equations. Does it have a solution? Well, yes, no. If no, then we say, all right, let's assume it's 1. Well, does it have a solution? Yes, no, and so on. So we can move up. Okay, good. So we can solve this relaxed problem. Does that help us? I mean, it's nice to solve a relaxed problem, and in the end, we get 2 vectors out of it, 2 polynomials, lambda and h. Does that really help us? Right. Well, yes, right? Because, let's put it like this. If h really, we could easily check if this is true. Right. Once we have our h, we can easily check if this is true. And if it is true, then we have solved this problem. Right? If it is true, we have solved this problem, which is the problem we wanted to solve. All right, good. Yeah. So is that all we need to know about this? We want to give guarantees. We want to give guarantees that we correct up to so many errors, t errors, say. Right? So we have to guarantee that if there are not more than t errors, whatever t will turn out to be, we can guarantee that A, we will find a solution, and B, this will hold. Right? So 2 things to prove. Is that clear? That we have to prove those 2 things? So the first one first. When do we find a solution? When are we guaranteed to find? When can we guarantee the existence of a solution? Well, when can we do that? Let's look at this. Right, these are n constraints. Right. This is a system of linear equations with n constraints. If the total number of degrees of freedom exceeds n, then we cannot. Then we are left with something non-trivial after we solve the system of equations. So what's the total number of degrees of freedom? Number of degrees of freedom so we get the lambda as a degree of freedom. So which is degree lambda plus 1. And the other one is plus, what is this one? Plus k plus degree lambda, right? This is the total number of degrees of freedom here. And the reason is that this one should be minus 1. So this is total number of degrees of freedom. If this is greater than n, right? If this is greater than n, then we can guarantee the existence of a solution, a non-trivial solution. Then this thing will have a solution. Right? It's a homogeneous system of equations. So the 0 is always a solution, but that's not much good to us. So what do we get here? Degree lambda. 2 degree lambda greater than n minus k plus minus 1, right? Or n minus k. So the degree lambda greater than n minus k over 2. Does that remind you of anything here? Right. So this one is d minus 1 over 2, right? So, very interesting, right? Once upon a time, you learned that if we make less than d over 2 errors, we can correct that. Very nice. It pops up here, right? It pops up here out of the blue. The reason that it pops up here is, of course, the same statement that as long as we stay within d over 2 errors, we are guaranteed to be able to decode this. Okay, so this is one. So we know this one was the number of errors. If t is greater or equal than this, then yeah. So once, oh no, let's forget about the t. We can, if we proceed in this algorithm, hypothesizing the degrees of t, of lambda, once we've reached this number in the degree, there will be a solution. And we don't have to go further anymore. Okay. So that's the first one. So the second thing we have to prove is that, I shouldn't have done this, that as long that for some t, yeah?
Do you need more constraints than the degree of freedom or less constraints?
You want to guarantee a solution, right? If you have more constraints than degrees of freedom, then since it's homogeneous, you usually would be stuck with a zero solution. Everything's zero, which is no good to us. It solves this problem, but it doesn't give us any information. Is that right?
Why does it have to be that the degrees of freedom has to be greater than the constraints?
No, it's so the degrees of freedom, well, okay, it's true, right? We could get lucky. We could have redundancy in the system of equations, right? And if we get lucky, that's just for the better. And actually, you can show that you do get lucky if very few errors happen, right? Then this will have low rank, right? You can show that. But short of knowing much, we want to guarantee, I just want at this point in time to guarantee that there is a solution. There is a non-zero solution to this system of equations, and the degree of lambda is not more than d minus 1 over 2. Right? There is a solution with a degree of lambda being upper bounded by this. Yeah, no. The degree, so once this is satisfied, right? Once this is satisfied, I guarantee you there is a solution. That means the smallest solution is guaranteed not to be larger than that. There are, of course, many, many more larger solutions. There are many solutions of larger degree here, which we are not interested in, since we are interested in the minimal degree lambda. So this is an upper bound on the minimal degree lambda. Right. Okay. So now the other one. So now we want to make a statement about this one here. When can we guarantee that that our relaxation didn't matter? Right? Despite our relaxation, our solution that we find, that in the solution that we find lambda divides h. How can we guarantee this? All right, so how can we guarantee this? Let's look at lambda xi yi minus h of xi. And we know this is 0 for all xi. We know that. We know that this guy here can actually be written as ci plus ei, right, minus h of xi is 0. This is just expanding this guy. We also know that we can write lambda xi times ci alone minus f of xi lambda xi is 0. We know that this is true too. Right? For some f, that there exists a f, right? So that this is true too. Then let's just subtract these two guys. Right? Let's just subtract these two things here. And then we know that lambda xi times ei, right? So the first two cancel, minus h of xi minus so we know this is true too. Yeah, sorry. Sorry, just in time. All right. So what can we learn from this? So what is the degree of this? Right? What is the degree of this? Well, this guy here, let me write it somewhere else. This guy here, well, this guy had degree h was less than n minus k plus degree lambda less than k. Less than k plus degree lambda. Well, that's because we set up that problem that way. And we know that this guy degree lambda. Okay. We know that. So this whole thing, let's call it S. We know is 0 for degree as less than degree lambda. Okay. So why does that help us? Well, let's look at the vector. Now let's look at all the positions. All right, let's look at the vector where we have in the vector we have lambda xi ei. Right? And now the fundamental question, what is the weight of this vector? Right? At most. Right? What's the weight of this guy at most? 12 seconds, kick in. Well, the weight of this vector is definitely not more than the weight of the arrow, right? Because every time the arrow is 0, a weight drops out. Well, that's then most t. Okay. What is the weight of this vector? So here we have a vector on the other side, S of xi, a vector on the other side. What's the weight of this guy? That's just a polynomial of degree at most k plus degree lambda minus 1. So we have that the weight of this vector is n minus k plus degree lambda minus 1 plus 1 maybe, because of the minus.
Greater than or equal?
It's greater than or equal, sorry. Otherwise I would have been in trouble in a second here. Yeah, so what does that mean? So actually this one is nice to rewrite. Is equal to d n minus k plus 1 d, I really should have done it like this in order not to, it's d minus degree lambda. So what can we learn from that? So we know this is true for all positions. All right, so if this is true for all positions, then so if d minus degree lambda, actually this is t, right? Because the way it was defined, t was the number of arrows, right? And the arrow locator was just defined to have degree t, right? The arrow locator was just x minus xi over all positions where we had an arrow, so there are t of those positions. The degree of lambda is equal to t. So now we take this. If d minus t is greater than t, right? So if the weight of this vector is greater than the weight of this vector, then we have a problem, because that cannot be. Because by this identity, the weight of these two vectors is equal. So what is the way out? What's the way out? Yeah, so if this is true, then S of xi, I claim, has to be 0, and lambda of xi times ei has to be 0 too, right, for all I. Right. That's the only way out of this, right? Because obviously this was allowed, right? If we really did find what we wanted to find, namely an arrow locator here, then this vector, we said it has to be less than t. It can be less. In particular, it can be 0, right? If this is indeed an arrow locator. And if our relaxation didn't matter, that means the h that we find is indeed a factor, is factors as that. If the relaxation didn't matter, then s would be 0 too. So that is a fair solution, right? That's a possibility. And if d minus t is greater than t, right, then this proves this is the only solution that is feasible. That's the only solution we have. So what that means is, if t less than d over 2, right, then the relaxation doesn't matter. Doesn't matter. And h of xi is equal to lambda of xi times f of xi. Yeah. All right. So is that clear? That's two very simple yet nice ways to prove things. Right. Here we guarantee the solution. Right. Here we guarantee the solution. Here we guarantee that solution is correct. Namely, if not too many errors happened, if less than d over 2 errors happened, right, then relaxing the original problem here to this other form which we could solve does not change the solution. Right. That's what's proved there. All right. About 1/3 looks puzzled, or half looks puzzled, I would think. Half looks puzzled. Is there any way I can explain that better? Think. Let's just go through the steps quickly, right? We had problem number 1. Problem number 1, which is a nonlinear problem, but you sort of see that if we could solve this, we could solve the decoding problem. Right? So you see that. Anybody who doesn't see that? All right, you're smart guys. All right, good. If we can solve problem number 1, we are home free. We have solved the decoding problem. Fine. We cannot solve it. It's a nonlinear problem. Well, we can solve it in exponential time, but that's sort of little fun. So we relax it. We relax it into problem number 2. Well, all that we do, we multiply things out, and we do not require in our problem this anymore. Once we solve the problem, this anymore. Right? But now assume we have found. Now we have solved this problem. We have solved this linear system of equations. And after doing so, we have found lambda and h. Okay, they are lying on the table and looking at us. Now what? Are they any good? Particular, since we cannot, a priori, we cannot guarantee that this relaxation didn't completely destroy everything. So we have solved the system. Now those two things are lying on the table, looking at us and asking, what am I? And in general, if there's an arbitrary amount of errors happening in the channel, actually they do not mean much. Right? They do not mean much. But now I claim that, well, if not too many errors happened, but if the number of errors is bounded to be this, less than half the minimum distance, then actually I claim it did not matter if we solved the relaxation or the original problem. And the argument is roughly this. It goes like this. Here we start. We have solved this. We have two polynomials, lambda and h, so that this is true for all xi. Okay? We know that we can write it like this. That's just by definition of yi. Just expanding the yi into this. Okay, good. We know that this is true by the definition of the code. The ci is the evaluation of f of some polynomial f. Right, so we can write this just by definition of the code. So once we have these two guys here, we can subtract them, get here. Right? So we know that we have solved the following problem. We have found lambda and h, so that there exists the polynomial, there is guaranteed to exist the polynomial f, so that this whole thing, namely s of xi, that s is a polynomial of degree at most, what did we have? K plus degree lambda plus 1, minus 1. Right? So that's a semi-hairy step here. Is that clear? That we can guarantee the existence of a polynomial s of degree at most k plus degree lambda minus 1. Right? So that this equation holds. Right? Once we have solved this, we can guarantee the existence of this. That's what we say. Right? We can guarantee the existence of this. So now look at this. Right? If you write this out for all i's and put it in a vector, what's the weight of this vector? Well, it's at most t, because all the other e's are 0. We do not know if lambda is an error locator. It is 0, but we do not know that yet. All we know is at most t. Right? This is on this side, so that vector has weight at most t. On this side, the weight of this vector is at least this. Just by evaluating a polynomial of this degree, this is the maximum number of zeros we can get. Okay. So now we have two equalities, this one and this one, but obviously the two vectors must be the same. Right, so how can these two vectors be the same and still satisfy these two inequalities? Right. Good question. How can they be the same and still satisfy this inequality? And I say if t is less than d over 2, then if t is less than d over 2, then the weight of this vector would have to be larger than the weight of this, if they are non-zero. Right? If they are non-zero, this would have to be larger than this, because then d minus t would be greater than t. If this is true, this implies this. Right? If this is true, this implies this, which implies that the weight of this vector would be larger than the weight of this vector if they are non-zero. Right? But how can that be? Answer is cannot. Right? Cannot be, hence they must be zero. Both vectors must be zero completely. Which means this is an error locator, because otherwise this wouldn't be zero. And this one, where did I write it? Somewhere I wrote it. This relaxation. So S of x, where did I write it? Here, right? So this S, right, has to be 0 too. If this S is 0, then h of xi is exactly this. Means factors in the way we want it to. So that's all I can say. I mean, I could say it again, but it's exactly the same words. And there's a limited benefit to even the repetition code. Okay, so beautiful, right? We have brought down the entire decoding problem for Reed-Solomon codes to solving a linear system of equations. Namely this one here, or this one in short form, which, well, is no problem at all in the grand scheme of things. And that's the other thing that makes Reed-Solomon code so beautiful, right? There exists encoding, there exists decoding, there everything that we want to. Okay. Let's see. Yeah. All right. Let me do one more thing about the decoding, just to bring it down a little bit, to talk a little bit about complexity. Solving this linear system of equations has been subject to research for 30 years, 40 years, something. So it started out with an algorithm which essentially solved that linear system directly. Was formulated a bit different, but that's what it is, called the Peterson-Gorenstein-Zierler algorithm. All right. They realized it was a polynomial time decoding algorithm, a nice decoding algorithm. Then Berlekamp, I should write down the name. Berlekamp came up with a fast algorithm, an n-square algorithm. Massey had its own formulation, his own formulation of that algorithm, which sort of was a bit more streamlined, I think. And there was a later version, Berlekamp-Welch. The complexity of these algorithms is all roughly the same. It's all n squared, roughly. Which solved this here. And then there's roughly nothing happening for 30 years. And after 30 years in Madhusudan, made the next serious dent in the decoding history of Reed-Solomon codes. So he found a way to solve this problem even beyond half the minimum distance. And in hindsight, it's a very nice and very simple trick that he used. All right? So we started with the following. We started that, well, if we have no errors, then the pairs of points yi, xi, yi lie on this curve. Right? That's other way to formulate what we said, right? Namely that yi minus f of xi has to be 0. Okay. We said, well, if there are no errors, all the points that we receive lie on this curve. Because there are errors, we have to multiply this with an error locator and say this is 0 for all xi, yi. So this was problem number 1. The relaxed form was lambda xy minus h of x 0 xi, yi. Okay, that's how the way we took. So what did Madhu do? Very clever. He said, you know what? I mean, all that we have to do is annihilate the effect of the error, right, in this. The lambda, the whole reason for that lambda was to annihilate, so to take out the error influence out of this interpolation formula, to allow for a few errors to happen, which we can put in lambda. Now Madhu said, well, what about we take a polynomial in 2 variables? A polynomial in 2 variables, then same thing, right? If no errors happen, then all the points xi, yi will lie on that curve. If a few errors happen, then let's find a lambda xy and 2 variables of some minimal degree, some very small degree, so that this is still satisfied. Right? And the problem is entirely the same. And this one you cannot solve either. Right? You cannot solve either. But again, you can solve the relaxation minus again, you can solve the relaxation. This is again a linear system of equations and the coefficients of lambda and psi now. Right? And once you solve this linear system of equations, actually this one you can more handily write simply. Now there's no way to distinguish the y anymore, since both sides anyway depend on y. Find a polynomial in 2 variables such that this is 0 for all xi, yi. This is his central problem. Right? This is his relaxation. Find a polynomial in 2 variables, which evaluates to 0. And he says, well, and then he has essentially the same proofs we have here, which is a bit more technical, but not much. And I'm sure you all can. I'm sure you can come up with this if you sit down at home. There's no. Let's put it like this: there's no heavy machinery in it. There's no heavy math in it. There's a lot of being clever in it, but there's no heavy math in it. Which he can now guarantee that q of xy, if t is less than n minus square root of 2k, is that right? 2kn. Then he can guarantee that y minus fx is a factor of q of xy. The same thing we want to guarantee. Right. And like I said, the proof is very clever, but no heavy machinery in it. It's no heavy algebraic geometry or any of this stuff in it. It's high school algebra, the proof. Well, freshman college algebra. So that's what happened here. So it took 30 years, and the computer scientists to solve that problem. All right. Okay. All right. Yeah, that was not all I wanted to say, but that's all I have time for. There's 1 minute left, so there's no point in starting something now. Do you have any questions about any of this? I should say that this 2 one can get rid of. But that takes a little bit more machinery. So the 2 one can get rid of, but that's a bit more heavy. All right, so thanks so much. That's it.